where we left off in the last lecture. So this, up to this point, we have discussed about the kinematics of SHM, velocity and acceleration and initial phase condition and all these things. Now we start looking into dynamics of SHM and solving spring mass type of systems and understanding the oscillations and time period in terms of SHM and all these things. So what we've seen is that from the equation of SHM, we have the instantaneous velocity of the oscillating particle is given by this kind of equation. And from these, we can see that initial position is a sine phi, initial velocity is a omega cos phi at t equal to 0. So therefore, we get the amplitude and the phase constant as these quantities. Okay, but then we'd also seen that the acceleration is minus a omega square sine omega t plus phi. So now comparing the first and the third equation here, the x versus t and the a versus t, we get that the acceleration which we can write as d2x by dt square is minus omega square x. So this is the dynamical condition for SHM, or net force. So F can be written as minus m omega square x, or you can see that at x equal to 0, so it's an equilibrium position. And at x equal to x, F is equal to minus kx, which means that the magnitude of the force is proportional to magnitude of displacement, and direction is opposite x. So it is a restorative force. So that way we say that in words, the dynamical condition becomes like this, that there is a restorative force proportionate to displacement from the mean position is required for SHM. Any system which has this condition, that it has a restorative force, that means it tries to restore it back to the mean position, proportional to the displacement from mean position in magnitude, that kind of system will perform SHM. Okay, so now we'll see the most simple and basic example of this kind of a dynamical system is a spring mass system in a horizontal situation. So let's say we have on a smooth horizontal surface, we have attached a spring to a block like this. Okay. So given mass of the block is let us say 4 kilograms, and the spring constant is, let's say, 1 Newton per centimeter. So the system is a smooth surface, is initially at rest with the spring relaxed. Now at t equal to 0, the block is pushed against the spring. So as to compress it by 2 centimeters, okay, and released from rest. So first of all, show that the block performs SHM and find its time period. Find the amplitude, the maximum speed, and the maximum acceleration during SHM. And finally, write the equation of x as a function of time t, where x is the extension of the spring. Okay, so just take down the data of the question first. We will discuss this in detail. Then I will give you some questions to solve yourself also. Okay, so let's understand this question. So let's say this is the natural length position. Okay, Diti, I'll take you back to that, don't worry. What I'm doing is initially I'm pushing the block against the spring through a displacement. So I'll take that as minus 2 centimeters because I'll take this direction as my x-axis. Okay, like this. This is my x-axis. Okay, and releasing it from rest. So now you can see that at some subsequent time, whether the block is over here or whether the block is lit over here, we'll have a situation where if the displacement is a negative x, the force acting on it is positive. If the displacement is a positive x, the force acting on it is negative. Okay. So on both sides of equilibrium, we can see that. So if this is my x equal to 0 position, whenever I'm over here at x equal to some negative value, the spring force will be pushing it like this, giving it an acceleration. So for a negative displacement, it will have a positive acceleration. And similarly, for a positive displacement, the spring will be pulling it back. So here x is positive. So acceleration is negative. So whether you look at this FPD or this FPD, you can see that kx is equal to ma and a is minus d2x by dt square because a is opposite to the direction of x. So we have the equation d2x by dt square is equal to minus k by m x. So we have the dynamical condition for SHM. Where omega square is nothing but the spring constant divided by mass. So the spring constant was 1 Newton per centimeter. So in newtons per meter, it will become like this. And the mass was 4 kilograms. So you can see omega is 5 radians per second. And time period is this. So in this case, okay. So that is the first part. So that it performs SHM. So answer to that is this. It satisfies the dynamical condition. So we show that and find the time period. So approximately this kind of time period. So I'll just take you back to the question once, complete noting down the data, and we can come back to the solution. Yes, Tej, I'm doing that. Yes, so that's correct. You'll so first of all, you've shown that it's an SHM and you got the value of omega square of time period. Kanishk and yes, correct. The amplitude is correct. You have to just give the units also, make sure. Kanishk, give the values of velocity and acceleration with the proper units also. Okay. So now once you have understood this, that this equation is being satisfied, okay, that d2x by dt square, so for the second part, is equal to minus omega square x, where omega we just saw is square root k by m. Okay, so that was numerically working out to be 5 radians per second. So now we know that this implies that x is a sine omega t plus phi, and therefore v is a omega cos omega t plus phi. Now we'd also seen that at t equal to 0, at the starting position, x naught's value was how much? Minus 2 centimeters. We had compressed it by this much, and we'd released it from rest. So from that now we can see that when we substitute this, we'll get amplitude as 2 centimeters. Okay. And phi is tan inverse of x naught divided by v naught by omega. Now here we'll notice one thing, that this is tan inverse of an undefined quantity. Okay. So it can be, according to this, it can be pi by 2 or minus pi by 2. But now you have to understand that x naught, which is a sine phi, is negative. Okay, and v naught, which is a omega cos phi, is 0. So this tells us that phi will be minus pi by 2. will be minus pi by 2 and not plus pi by 2. So our phase constant will be like this. So our x as a function of time will become 2 sine 5t minus pi by 2, where x is in centimeters, t is in seconds. Or we can therefore also write x as minus 2 cos 5t. And from that we can also see all these things, that once you got the amplitude, see that so maximum speed is 10 centimeters per second or 0.1 meters per second, and maximum acceleration is 25 into 2, so 50 centimeters per second square or 0.5 meters per second square. So again, x as a function of time, maximum speed, maximum acceleration, amplitude, everything is solved this way.
Excuse me,
Yes. Sorry, I didn't get the question.
sir. I have a doubt. That is, how
Yeah.
did you get the value of phi as minus pi by 2?
How did we get the value? Phase
Phi.
constant. Okay, okay. So see, once you got this d2x by dt square is minus omega square x, you know that it means that x is a sine omega t plus phi, right? In general, and v is like this. Okay, so at t equal to 0, what will be the value of x? It will be a sine phi.
Yes, sir. Yes, sir.
Okay, and what is the value of v at t equal to 0? It is a omega cos phi, and that is given to us as 0 in the question, because it starts from rest.
Sir, I got it. Got it. Got it. Got it.
Okay, so sine phi is negative and cos phi is 0. That's only possible when phi is either 3 pi by 2 or minus pi by 2, like that, odd multiple
Yes,
of
sir.
pi by 2.
N pi by 2.
Yeah, n pi by 2n plus 1 pi by 2 actually.
Yeah, yeah. Okay. Yeah, got it. Got it. Got it. Sorry, sir. Then it will be
Yeah.
applicable even for the pi by. That's not possible. Yeah.
Yes, yes. Okay. Okay, I'll scroll up the. So anyway, hope all of you have understood the concepts related to this question, how we calculated all the things, not only the value of omega from the, actually to start with, what we do is we solve the free body diagram. So the first step is we solve FBD to get the condition of SHM. What is the condition of SHM? That F should be equal to, I mean, it should be a restorative force proportional to displacement. So it should be a minus kx type of force, including the algebraic sign. Or d2x by dt square should come out to be some negative quantity into x. And that negative quantity is omega square. So from that, we get the time period. So that was the first step. And once you've done that, you got that equation and you know the value of omega. So you know that x is an SHM parameter. So the next thing is you need to calculate the amplitude and the phase constant. So remember, always amplitude and phase constant comes from the initial conditions. That is the value of x and v at t equal to 0. So that is what I've done in the second part over here. X naught and v naught's value is substituted. And from that, we have got this thing. We have got the amplitude A as 2 centimeters, and we've got the phase constant is minus pi by 2. Now again, it's a little bit technical why the phase constant comes out to be minus pi by 2 and not pi by 2, because x naught is negative. So A sine phi has to be negative, whereas V naught is 0. Okay, so hope this question is completed now. You've finished writing down everything. Okay, very good. So let's look at another example now. So spring mass systems are like, what most of the questions in SHM are going to be about. One type is the spring mass systems and the other is going to be the pendulum type system. When we come to that later. So let's look at another example of spring mass system. So similar setup, but this time we'll have a combination of springs. Two springs attached in series from this side and another spring attached from that side. So now given that K1 is 6 Newton per centimeter, K2 is 3 Newtons per centimeter, K3 is 2 Newtons per centimeter, and the mass of the block is, let us say, 1 kg. So all springs are in a relaxed state in the position shown above. Firstly, what we have to do is show that if disturbed from the equilibrium, position, the block will perform SHM. And find its time period. And the second thing is that if from the position shown, the block is pushed by a sharp impulse. We apply a sharp impulse in this direction of magnitude 0.2 Newton second, at t equal to 0. Find the amplitude and equation of SHM. Okay, so this is almost an identical question, but with just the addition that there is a combination of springs, so we'll have to deal with that. And also here the system is initially pushed with an impulse. So instead of having initial displacement from mean position, the block has an initial velocity at the mean position. Yes, Yash, I will just verify your answer. So what we'll see here is that in this system, we can reduce the combination of springs into a single equivalent spring by doing this. This is a series combination. So we can replace it with a single spring of this kind of constant. So when we do that, we get 2 newtons per centimeter. So next step, replace that combination of K1, K2 with a single spring of K. And now you can see that this is such that equivalent spring constant become K plus K3. So this can further be reduced to, we can keep the equivalent spring on either side. So this system is equivalent to this. So this is doing SHM with omega equal to square root of this. So the omega for this system is 20 Newton, 20 radians per second. So the time period is approximately this much. So I will take you once more through the basics of series combination and parallel combination of springs. Okay. But first, just make a note of this. Now you can also see that because of the application of the impulse at t equal to 0, this has a velocity in this direction of j by m, but it is at natural length position. So x naught is equal to 0. So this impulse that we had applied was 0.2 Newton second. Okay. So 0.2 divided by 1. So it will have 0.2 meters per second or 20 centimeters per second initial velocity. That is what we'll use to find the amplitude. Now, okay, V naught is plus 20 centimeter per second and x naught is equal to 0. And omega is equal to 20 radians per second. So using this and this, find amplitude phase constant equation of SHM. Okay, so you'll see that we'll get the amplitude as 1 centimeter. Okay, and we'll get phi as tan inverse of 0. Take that as 0. So our equation of SHM will become A sine omega t. Now the amplitude is 1 centimeter and omega is 20 radians per second. Impulse is equal to change in momentum, Yash. Okay. So just finish writing this down, then I'll tell you a little bit about the series combination in more detail, how we can derive that formula. Okay, so let's see about the series combination. So we have a combination of two springs joined end to end like this, which have natural lengths L1 and L2 and spring constants K1 and K2. And we are comparing that with a single spring. This is a constant K and natural length L. Now suppose this combination is stretched out such that this end is given a displacement of x by application of some force. Okay. And as a result of this stretching out, this spring gets extended by x1 and this spring gets extended by x2. So we have this type of force picture. So from this point's equilibrium, we have K1 x1 is equal to K2 x2. From this, we have that is equal to F. And we have x1 plus x2 is equal to x. Whereas the same thing here we have kx equal to F. So if we have to compare this set of equations, we will see that from this we have x1 is to x2 is K2 is to K1 and x1 plus x2 is equal to x. So x1 is K2 upon K1 plus K2 into x. X2 is K1 upon K1 plus K2 into x. So f, which is equal to K1 x1 or K2 x2, can be written as so we can see K is equal to K1 K2. This is the idea of series combination. So I'm sure you have seen this before in system of particles, work energy, etc. But in case you need to recall this concept of series combination, you can quickly just go make a run through of this. Then we'll discuss about the parallel combination also. Okay, now similarly, let's look at the parallel combination.
Excuse me, sir. Just a minute.
Yeah. Okay. Okay, so done with this now. So parallel combination of springs. So there are actually two types of arrangements possible. In this particular question that we did above, we utilized one arrangement, but I'll show you both of them here. So one arrangement of a parallel combination would be like this. So one could be that there is a combination of springs attached from the same side, attached between the same wall and the same object. So this would be a parallel combination. Another combination would be that there are two walls on either side and two springs are connected on either side. So one should not confuse this second case with the series combination, because the series combination is very different. In the series combination, the springs are attached end to end, and then the block is attached on one side. So you can see it's quite different from this one. So series should not be confused with this. Okay. So in either case here, you can see that if you displace the block by x, both the springs get extended by x. Okay, so they apply a net force. So the equivalent K is K1 plus K2. And the same thing applies here also. If we displace this by x, then this spring will get elongated by x. So it will apply a spring force like this. But on the other hand, this spring would have got compressed. So this will apply a pushing force like this. So again, on the block, you can see that there is a net force like this. Okay. So the same equation applies to both cases. So this and this both. Okay. The block can be moved in either direction. It will give you the same result. So for example, this is the natural length position. Now if you displace the block in this direction by x, both the springs are getting compressed by x. So they'll both apply pushing force. So on this block, there is a net force opposite to the displacement. Same thing. Okay, so this series and parallel combination is clear, I hope. Okay, now next thing we'll move on to is SHM of a vertical spring mass system. Let's say we've got a spring of constant K attached to a block of mass M in a vertical situation. Spring constant is, let's say, given as 12 newtons per centimeter. The mass of the block is 3 kg, and we take G as 10 meters per second square. Okay, now, initially, the block is in equilibrium at rest. So, first of all, we want to find the extension of the spring in equilibrium state. Second, show that if given a displacement, let's say a vertical displacement, from equilibrium state, the block performs SHM, and find the time period again. And if the block is pulled down by 2 centimeters from the equilibrium state and released from rest at t equal to 0, find the amplitude and phase constant of its SHM and find the maximum extension and minimum extension of the spring during this SHM. Okay. So very similar to the previous situation, the horizontal spring mass system, but the only thing we have to account for now is that at any instant on the block, there's a combination of two forces that is acting along the direction of SHM. There is spring force as well as mg. So you have to show that the net force, which is the vector sum of spring force and mg, the resultant force is going to be of that type, that it is going to be restorative. That is, it points to the mean position always, and it is directly proportional to displacement from mean position. Okay, so I'm just putting up the answers first. So what we'll see is that this thing, x of the spring in equilibrium will be mg by k. So that will be 30 newtons by 12 or 2.5 centimeters. Now time period will be 2 pi under root m by k. You see, in this case, the amplitude will become 2 centimeters. The phase constant will become pi by 2. Equation of SHM will be like y is equal to 2 sine omega is this. Where y represents the downward displacement from the mean position. So from that, you will understand that the maximum extension of the spring will be x at the equilibrium plus amplitude. So that is 4.5 centimeters. And minimum extension will be x at equilibrium minus amplitude or 0.5 centimeters. So I'll explain the working of this also, but please verify your answers if you have worked this out so far. So I'll give you the basis of this working in just a moment.
Excuse me, sir. Excuse me, sir.
Yes. What is the doubt?
Sir, K is given in Newton per centimeter, while
Yes.
G is given in meter per second square. So, don't we have to convert cm to m or m to cm here?
Yeah, you can do that also. Okay, you will get the same answer. Okay. So convert K to newtons per meter, that's 1200, and mg is 30. So when you do 30 by 1200, you will get 2.5 into 10 raised power minus 2 in meters. So ultimately in centimeters is the same thing. No?
Yeah, sir, I got the same answer. Yeah.
Okay.
Actually, I took meters as centimeters, so my answer was in match. So there was some silly mistake. Thank you, sir.
Okay. Yes, Shitesh, to answer your question, if the block is released from a position where the spring is in natural length initially, then also it will perform SHM, but it will have a different amplitude. Its amplitude will actually become 2.5 centimeters, or mg by k in this case. Okay, so let's understand this way first. Okay, that let's say this is the equilibrium position. So the acceleration of the block is zero over here. So at this point of time, the spring is stretched by, let's say, whatever x for the equilibrium position is. The spring force has to balance mg. So that's how we are getting the equilibrium situation, which works out to be 2.5 centimeters. Okay. Now from here, what we are doing is initially we are pulling the block down by a further displacement. So what I'll do is I'll take this as my y equal to 0. Okay, this is the origin of the SHM, that is the mean position. You see that we have taken it initially to a displacement of y naught equal to 2 centimeters and released it from rest. So first of all, to show that in general it will be in equilibrium, this is our equation 1. So at any general time t, suppose the block is at a position like this, that compared to our equilibrium position, it is at a displacement of y. So at such a situation, we'll have an upward acceleration such that now x will be equal to x at the equilibrium position plus y. Okay, so that is mg by k plus y. So at this position, kx minus mg is equal to ma. So k into mg by k minus plus y minus mg is equal to m. So this is the general situation at some time t. So at t equal to t, when y is equal to y, so the extension of the spring is the equilibrium position plus the additional downward displacement, because I'm taking my y-axis as downwards. So comparing the two equations, you can see here that ky will become equal to ma and a is minus d2y by dt square. So you got your SHM equation now. So from this we got our equation that d2y by dt square is minus k by m into y, where y equal to 0 is the mean position and y is the displacement. Downward displacement from mean position. So this is the first part, that we have shown that it's an SHM, and you can see that this is an SHM with omega square equal to k by m, which in this case worked out to be so this shows that y will be some amplitude into sine of omega t plus phi, where omega is 20 radians per second. Okay, so note down up to this step, then we'll calculate amplitude and phase constant from from the given initial conditions. So this is the mean position here, this one. This is the initial state, that is what is happening at t equal to 0, and this is some general T equal to T kind of situation. Okay, so you've now figured out from this that how to find the amplitude and the phase constant. So you can see that at t equal to 0, y naught is given to us is 2 centimeters. Okay. So a sine phi is equal to 2 centimeters and is released from rest. So v naught is 0. So a omega cos phi is equal to 0. You can see that the amplitude will be 2 centimeters. Okay. And a phase constant pi by 2, because from here you can see that cos phi is 0, sin phi is positive. So y as a function of time is becoming 2 centimeters sin 20t plus pi by 2. So the extension of the spring is equal to equilibrium extension plus y. So this is the extension of the spring. This is the SHM parameter in centimeters. So x is maximum value and x is minimum value. So as the block is doing SHM, it's oscillating between one amplitude below and one amplitude above. But as far as the spring is concerned, here the spring has an extension of 2.5 centimeters. So here the spring has a maximum extension of 4.5 centimeters. And here the spring has a minimum extension of 0.5 centimeters because this is the equilibrium state. Okay, so this is how you can make sense of this. So with this we conclude this lecture today, and with this we conclude SHM of spring mass systems. So next lecture we'll be moving on to the final part of SHM, which is the pendulum systems and angular harmonic systems, including simple pendulum, physical pendulum, etc. So that will be the last part of SHM. Okay. So please work out questions from HC Verma at least up to question number 28 from the SHM chapter. Okay, we'll discuss further in the next lecture.